Hello, everyone, and welcome to the last section of this chapter. In this last section, basically what we're going to do is look at limits where some of those functions will involve more advanced functions. So these transcendental functions, so like the exponential function, the logarithmic function, sine and cosine, and all the other four trigonometric functions. So the first thing I'm going to do is I'm going to first review the basic graphs of these advanced functions. So you only need to know to compute any limit in this chapter, and even in a Calculus 1 course, you only need to remember the basic graph of the exponential function, the basic graph of the logarithmic function, both base e, and the basic graph of the sine function and the cosine function. And with a good knowledge of these four graphs, you can really attack any limit involving any advanced equation involving those terms. So the first graph we're going to review together is the graph of the exponential function, e to the x. So that's the graph we're going to look at. So the exponential function is defined everywhere. So the domain is everything. The range is from 0 to infinity. It never reaches 0. And actually, one thing you can see on the left side here, boom, okay, we have a vertical asymptote at y equals 0. So this means what? This means that the limit as x goes to minus infinity of ex is 0. Or another way to say that is to write down simply that e to the minus infinity is 0. I'm going to write that at the end, like all the important point. The only point you should also know is that your function at 0 is equal to 1. So e of 0 is 1. And the function goes up forever. So here at the other extreme end, when x goes to infinity, okay, boom, the function will go to infinity. So this function does not go to any horizontal asymptote. So the way I like to do this is by writing the limit as x goes to infinity of ex is infinity. So a couple of pointers that we're going to be using a lot that summarizes what you should know from the basic exponential function. So here are the thing that you really need to master. So we're boom. Okay, so as a remark, about a bunch of remarks here. So first, okay, the value of the function at 0 is 1. So this is the only output that you need to really know precisely. It's the only nice output that we know, like, okay, at 0 is equal to 1. And one thing to notice here, if you pick an input slightly bigger than 0, you're going to get an output slightly bigger than 1. You can see this on the graph here, like using a dot, just like, just slightly bigger, you're slightly higher. And same thing for if you pick a value slightly smaller than 0, e to the power 0 minus will be equal to a number very close to 1 but smaller. So we're going to be using that. And here with the limits that I've mentioned earlier, so e to the power of infinity is infinity, and e to the power of minus infinity is minus infinity. Again, here I want to just stress, like, just as a remark here, I've mentioned this a moment ago, but I forgot to write it down, but the domain of ex is everything. So from minus infinity to infinity. So there's two important limits to compute. First, going to minus infinity is 0, and then second, going to infinity. So remembering the very important connection between open endpoints of the domain and important limits to compute. And here I'm just using the graph of the function to compute, okay, these, well, not compute, but identify these limits. So that's all that we need to remember for the exponential function. Let's move now next to the logarithmic function. So the next graph that you should recall is the graph of the logarithmic function. Okay, so for the logarithmic function, might as well write it down, but the domain of ln of x is from 0 open to infinity. So again, here right away, so there's two open endpoints. So there's two behaviors that you want to study. What happens when you're getting closer to 0 on the right side, and what happens when you're going to use very big inputs, so going to infinity. So with the graph here, let's see what happens when you're approaching a 0 from the right side. So here on the right side, what we can see is we have a vertical asymptote at x equals 0. So poof. So here's the vertical asymptote of that function around 0. Oh, sorry, I'm just having a hard time here. Yeah, come on. You're not seeing this. You're just going to see the end product. But anyways, so that's my vertical asymptote. So this means that the limit as x approaches 0 plus of ln of x is equal to minus infinity. So since we're there, might as well talk about what happens if you're on the left side. Well, if you are on the left side, so if you have a limit and you're trying to compute the limit, okay, I'll change color here. I'll put it in red because it's so bad. But what happens if you compute the limit as x approaches 0 minus of ln of x? Well, the function is not defined, so this limit is undefined. Okay, so there's nothing here. And of course, if you compute a two-sided limit, you're going to get does not exist. Okay, so we understand what's going on around the logarithmic function. So another thing you should remember, so then what about going to infinity? So this function does go to infinity, so it's going there humbly, it's really humble, but this function will go, it's not going to an horizontal asymptote, it goes up forever, boom, okay, so it goes to infinity. In other words, if you're writing that using the limit notation, so the limit as x goes to infinity of ln of x, you're going to get infinity. We're going to summarize that with symbols in a moment. The only input that produces a nice output, it's at 1. So we've already used that fact in chapter 1. At 1, the function is equal to 0. So that's the only root. So boom. Okay, so boom. So here's my only root for the logarithmic function. So now I'm going to summarize this with a bunch of remarks. So what happens if you're dealing with the logarithmic function? So like I said, so here we go, copy. Sorry, you're not seeing this there. So boom. So the first thing is ln of 1 is 0. So that's the only output you can compute. So, and it's really typical, like any nice input that produces nice outputs will be using the fact that you know that to play around it. So if you pick an input slightly bigger, okay, you're going to get an output slightly bigger than 0. So ln of 1 plus is 0 plus. If you pick an input slightly smaller than 1, you're going to get that ln of 1 minus is 0 minus. So ln of infinity. So since the limit goes to infinity, we can write directly that it's infinite. Ln of 0 plus is minus infinity. Again, using the graph here. And ln of 0 minus, that's obviously undefined because you're out of the domain. Okay, so here, as soon as you're not in the domain, we use the undefined symbol. And that's all you need to know, okay, for the logarithmic function in order to address limits involving logarithmic terms. All right, the next two graphs are the sine and the cosine function. So we're going to look at sine first. Okay, so remember for sine, the way, if you don't have access to a graph, the way I like to sketch it from scratch, I know sine of 0 is 0, and then it first goes up to 1 until pi over 2, and it goes back to 0 at pi, and then it does the same bump, but in the negative zone, so sine of 3 pi over 2 is minus 1, and it goes back to 2 pi afterwards. And that's one complete cycle. And then, of course, it just repeats forever. And meanwhile, the cosine function at 0, it starts at 1. It goes down to 0 at pi over 2, down to minus 1 at pi, back to 0 at 3 pi over 2, and then back to 1 at 2 pi. So we have like this V-shaped thing. And then, of course, it repeats itself forever. Both function, their domain is everything. So it's R. It never crashes. So, of course, with the domain, with the open endpoints being the infinites, you wonder what happens when x goes to infinity or minus infinity. Well, both functions, they're not going to get closer to any horizontal asymptote. Both functions, they don't go up forever or go down forever. Both functions oscillates between -1 and 1 forever, never getting closer to anything. And this is why, if you're computing the limit as x goes to infinity or minus infinity of the function sine or cosine, you get does not exist. So if you have a computation where you're plugging infinity inside a sine function, sine of infinity, sine of minus infinity, cosine of infinity, or cosine of minus infinity, all of them does not exist. Okay, so that deals with the open endpoints of those domains. What you should know also from those graphs, or the way you should be using those graphs, is that there's a lot of nice inputs that gives you nice outputs. Like for example, for the sine function, we know sine of 0 is 0. So that's a nice output. As soon as you have a nice output, then I can play with what happens if you pick an input slightly bigger or slightly smaller. So if you pick a number slightly smaller, you can see on the graph that sine of 0 minus would be 0 minus. And if you compute sine of 0 plus, you're going to get 0 plus. So a number slightly bigger. Again, if you need to see this, just use points, on the graph. So same thing for, let's say, pi over 2. I'm not going to do all of them. I'm just going to go over some of them. But since you know that sine of pi over 2 is 1, then you might wonder, what's up if you pick something smaller? Well, if you pick something smaller, sine of pi over 2 minus is 1 minus. And actually on the plus side, so this is a fun one for me to use on exercises, sine of pi over 2 plus is also 1 minus. You get outputs that are smaller than 1. And of course, that's kind of obvious since the range of sine or cosine are are between -1 and 1. So you cannot get numbers bigger than 1 or smaller than -1. So I'll just do another one for sine. So for example, sine of pi is 0. So sine of pi minus, look at this. This is a nice one. So a number slightly smaller than pi will give you a number slightly bigger than 0. Sine of pi plus is 0 minus. So again, just using the graphs, okay, to make those computation or labeling. So same thing for cosine. So there's other points where you can play that game here. I'm just going to do 3 points for both functions. So for cosine, we see that cos of 0 is 1. So if you pick something smaller, you're going to get 1 minus. So cos of 0 minus is 1 minus. Cos of 0 plus is also 1 minus. I love those ones where on both sides you get 1 minus. We know that cos of pi over 2 is 0, so we can play that game. Slightly smaller, look at this. Cos of pi over 2 minus is 0 plus, and cos of pi over 2 plus is 0 minus. I did another one here. Cos of pi is -1, just to show you what happens around -1. That's a fun one too. If you pick a number slightly smaller than pi, cos of pi minus is going to give you a number slightly bigger than -1, so you get cos of pi minus is -1 plus, and you get the exact same thing on the right side. Cos of pi plus is -1 plus also. I'm just doing 3 points, but there's a lot of them you can play with. Okay, so any nice points. So for both of them, any multiple of pi over 2 produces interesting points where you can play at the value and at the left and the right side of those values. And a lot of people say, well, what about the other functions? So the trick, my approach for every limit involving the other 4 trig functions, tan of x, which is sine over cos, secant of x, which is 1 over cos, and cotangent, which is cos over sine, and then cosecant, which is 1 over sine. Basically what I do, I just go back to their actual definition in terms of sine and cosine. So with just the graph of sine and cosine, you can deal with any limits involving any trig functions. If you have the other ones, just write them up as equations in terms of sine and cosine so that you can just focus on those 2 graphs. Of course, if you know the graph of tan, secant, cotangent, and cosecant, you can use those to help you out. But I think in terms of complexity, or if you want to, let's say, minimize the effort of things you have to remember, minimize the amount of things you have to remember, and maximize the things you can do, just remember the graph of sine and cosine, the 4 definitions involving sine and cosine for the other four trig functions, and you're going to be able like to attack a lot of those problems. Okay, so that ends the review of those four graphs, the exponential function, the logarithmic function, sine and cosine. And now, to some extent, this is all you need in order to attack. And of course, you also need all the stuff that we've learned in the previous section. So with the stuff that we've learned in the previous section and with the graphs of those four basic functions, four basic functions that are transcendental, so they're not that basic, we can attack a lot of those problems now. All right, that's it for that video. Bye-bye.